Okay, last time we talked about indefinite integrals. So we had some kind of a function along here. It was just maybe x, y is equal to x. You get a nice straight line slope, nice and linear. You want to find out what the area underneath it is? Well, that's well and good, okay? But here's the thing. Before, when we talked about indefinite integrals, we didn't actually talk about how much of a slice of this thing we're looking at, right? Because if you're looking here versus to infinity, you're going to get vastly different areas for this function, right? So you also have to define those things if you actually want to come up with a number. If you don't want to come up with a number, which in physics a lot of times we don't, you come up with an indefinite integral, and that gets you the new function, right? So if x was your function before, the new function after you take your integral is going to be x squared over 2, okay? And then also, don't forget, you don't know where you started, what the origin was. It could be shifted up or over or left or right, something like that. So you do have to account for that by putting a constant in, how much of a shift there is, okay, in your function. So, physics, we like to get new functions because we like to get new formulas for higher dimensional things and talk about how that works with other things, right? From position to velocity to acceleration, we can take integrals of things or derivatives of things and we can figure out how that changes the function, which, it's going to change for every different situation you have, okay? The function will stay the same, but maybe the details, your velocity changes, your position changes, your acceleration value changes, okay? But so for physics, when we take the integrals, we generally take indefinite integrals, okay? But a lot of times you want to know specifically what happens for one area, one slice of the pie. So if I wanted to know between, x is equal to 1 and x is equal to 5, how much area is actually under that part of the curve, we can do that too with integrals, okay? And actually the first thing you kind of have to do is take an indefinite integral. You have to figure out what the new function is, okay? So that's actually the first part of a definite integral. So if you have this function, first off you need to find out what the integral is, and we've done that, okay? But let's come up with a different function. Let's say our function is x cubed, okay? It has nothing to do with this anymore, okay? Entirely new thing. You got some kind of a crazy, thing like this. You want to know what the area under the curve is, right? So you have to then take and figure out the integral of this function. Okay, so if I take the integral of f of x, again, if we follow our rules, we bump the power up by 1, so instead of x to the third, we still have x, right? That follows on through. X to the third becomes x to the fourth because we bump it up by 1. We also divide by the new power, 4, okay? And again, if it's an indefinite integral, we have to add a constant, all right? One other thing I neglected to tell you before. I told you this with derivatives, what happens if you deal with a constant? Well, let me do that first. What if your function was just 1? It was a flat line, okay? What do? Well, if you're looking at this with respect, right, you're going to take an integral of the function with respect to x, you have to bump it up by 1 in the x direction, okay? So if your function was 1, right, anytime you get a 1 or a constant, right, basically you can look at this as multiplied by x to the 0 power. Why? Because anything to the 0 power is 1, okay? So you can plug this value in, this x to the 0 or y to the 0 or t to the 0 power, anytime you feel like it. Because anytime you multiply 1, which is what this is, by your number, you'll end up with whatever that number was originally, right? So you always have lurking out there, whether you realize it or not, some kind of that variable to the 0 power lurking out there, even if you've got a constant, okay? So this is actually the function we're looking at. It's 1 times x to the 0 power. So what do? Again, the 1 will just carry on through, right, because it's a constant. So x to the 0 there, we bump it up by 1. So we'll multiply that by x. Instead of 0, it's plus 1, so it's x to the first. And again, we divide by the new power, which is 1, okay? So neatly enough, what happens when you take an integral of a constant is you just get that variable. You get that variable to the first power. I'll make sure you guys can see this well enough. I think the lighting's getting weird in here. So the integral, good grief guys, so you keep writing the integral symbol and the f, right? Fancy f for the function. So the integral of a constant is actually the variable, all right? So let's go back to our previous example here. What if we had x to the third power? Well, if we take the integral of x to the third, we bump the power up by 1. We get the integral, again, keep doing that, right? the integral of our function is now 1 power higher and divided by the new power, okay? And again, we have no idea where it starts out on the graph because that information was lost. We're just looking at how the function worked. So this is what we get, okay? So this is the first step for a definite integral as well, all right? But we don't know the c, so we're actually just going to forget about it for definite integrals. Kind of get rid of it. It's kind of weird, okay? But it actually doesn't matter too much because you're figuring out the area under that area, so under that function, okay? So we don't have to worry about the offset so much. But now we've got our general function, okay? We've got our integral. What the heck do we do to actually find it for some value of, I said the example was between 1 and 5 earlier. Okay, so when we do this for a definite integral, we go from 1 to 5, okay? So the bottom number is where you start, top number is where you end, okay? And anytime you want to try and find a change in things, keep this in mind for later, okay? Anytime you want to find a change, and that's what delta means, okay? You have to take the final, where you end up, minus where you started, okay? So anytime you want to find the change in something, which is really what we're going to find here, we're going to find the change in area between 1 and 5, okay? Anytime you want to find that change in something, you have to take the final spot minus the, initial spot, okay? So final minus initial. So our final spot is going to be 5. Our initial spot is 1. So what we're going to do now is we're actually going to plug those numbers in to our function. But we can't do them both at once, can we? Okay, so what we need to do for this, now that we have our new function, is we have to take and plug in this number, the bottom number or the top number. It doesn't really matter, okay? Let's go ahead and do the top number, okay, where we end. Because again, we want the final first, okay? So this function, we're going to get, instead of x now, we get 5 to the 4th power divided by 4, okay? That's where we ended. So the integral of this function between 1 and 5, where we ended, our final position, that's our formula for it, isn't it? But we have to subtract from that, because if we did this, we would just be looking at everything before 5, okay? Up to 5, that's what that would get you. So we have to then subtract out where we start. And where we started was at 1. So again, we have to use this function, and instead of x, we put in place where we started, which is 1. 1 to the 4th power divided by 4. So you have to subtract out your initial from your final spot. And that right there gets you your definite integral. Okay? So let's do that for another function so you guys can see how this works. I'll leave this part up here. Let's get something else. So how about this? Let's just talk about plain old x. Okay? Let's go back to that really simple line before that we had. Nice straight line. Very simple. There's our function. We want to know the area between, again, let's say, 2 and 6, okay? We're going to look at the slice that comes between those two values. What is the area in this region, okay? So again, we have to look at our function as x. Anytime it doesn't give you the number, you have to assume it's to the 1st power, okay? So what is the integral of our function? The integral of f of x here. Again, we'll take the indefinite integral first. We want to know what the new function looks like. Okay? So we got to have that function to work with to be able to plug numbers into later. So the integral of this, we're going to bump the 1 up by 1 power. Okay, so it's now x squared. And we take and we divide by the new power 2. Okay? So x squared over 2, which is actually kind of cool because if you look at this, if it was straight over, it'd be a rectangle. It would just be height, right, times width, x times x, okay? That would be x squared, basically, okay, or some kind of a value squared. But we're taking the triangle of it, so it's actually half of that. So you get that here too, which is kind of cool. You get the relationship between, rectangular and, triangular shapes. Okay, or lines at a slope and what their area looks like. Okay, so here's our new function, again, plus c, but again, for definite integrals, we actually don't have to worry about that so much. All right? So here's our new function. Okay, so now we're going to look at it between, we said, starting at 2, ending at 6. Okay, so for that slice right there of the function, what's the area in that region? Okay, we have our new function, so now we can plug it in. And again, we need to start with the number that we end with, final minus our initial value, okay? So the function with the final number in it minus the function with the initial number in it will get us our total area for that slice, okay? So, final, x squared over 2, right? X is no longer x, so it's x squared over 2 was our function. We're looking at it for the final spot. Final spot we're looking at is 6. Okay, so it's 6 squared divided by 2. Now from that, again, we're not looking at everything that happened before 6, we're looking at everything that happened before 6 and 2, between those two, all right? So then we have to get our initial spot where we started. Again, our function was x squared over 2, okay? But again, we're not putting in x now because we know what our value is there. We have a definite value of 2, okay? So our integral from 2 to 6 for this particular function will be plugging the final value in for x here, initial value for x there. Difference between the two will give you the area under the curve for that little slice of the pie, okay? So that is what a definite integral looks like. It's very similar to an indefinite integral. In fact, you have to kind of do that first, all right? But the next step is just plugging the numbers in and chugging through. And remember, it's always final minus initial. Take your equation, plug in your final value to start, and subtract from that your initial value, okay? And that's it, at least for our class.